The surf cracks, and the water erupts in a shimmering cascade of blue, each wave a flickering pulse of light, as dinoflagellates ignite in the churn of the tide. Footprints dissolve in the glow, leaving only the whisper of phosphorescence in the dark. Midnight on a quiet Florida coast. A naturalist crouches, boots sinking into cold sand. The ocean's surface shivers with blue light where his foot presses the water. He bends closer, fingers trailing the glowing foam. A single wave crashes, blue sparks fly upward like scattered sapphire dust. The light isn't from the moon or a distant ship. It's born in the water itself. He records it in his journal. The sea burns when disturbed. Not reflection, not oil, a living fire. He collects a sample. Under his lamp, the water pulses with tiny, moving points of light. Each tiny organism, a single cell, emits light when squeezed or stirred. The reaction is chemical, not electrical. The same chemistry that powers fireflies on land, but in the ocean's dark. Naturalists had seen it before briefly, dismissed as mirage or superstition. Now it was undeniable. The blue glow wasn't random. It happened only at night when waves broke. The light was a defense, a sudden flash to confuse predators like fish or jellyfish. One theory says the glow startles them, giving the plankton a chance to escape. The same luciferin and luciferase molecules that make fireflies glow in meadows light up the waves here. The mystery deepened. Why did this happen only in certain places at certain times? Why did the glow intensify with movement? The naturalist noted the water temperature, salinity, and moon phase. He realized the plankton weren't always there. They needed specific conditions to bloom into vast numbers. The ocean itself had become a living lantern, triggered by the simplest touch. The glow in his sample was just the beginning, a single note in a global symphony of light. Cold water, your bare foot meets the surf. Sand grains shift. A sharp, almost electric snap asterisk, then liquid starlight. Blue light bleeds from the water beneath your toes, spreading like spilled ink in a dark room. It's not light from the moon, not from the sky. It's the ocean itself breathing. Each footfall, each breaking wave triggers a silent detonation. Dinoflagellates, billions packed in the water column, releasing luciferin. The friction of movement ignites the reaction. The blue isn't just seen, it's felt, a sudden chill of light on your skin. This is not accidental chemistry, it's a precise defense. When a predator like a small fish or jellyfish lunges, the physical disturbance triggers luciferase enzymes. The luciferin binds, emits light in a flash. The predator hesitates a split second in the dark. To the plankton, that pause is escape. The same molecules power fireflies in meadows, luciferin, luciferase, oxygen. But here, the ocean holds the reaction. It's a silent alarm triggered by touch, not wingbeat. The glow only appears where conditions align. Warm water, typically 25 degrees C, 77 degrees F, or above, rich in nutrients from runoff or upwelling. Salinity must be stable, around 35 parts per thousand, like Mosquito Bay's shallow, protected lagoon, where the water is only 1–2 meters deep. Heavy rains fertilize the bay, fueling blooms. Moonless nights are essential. Any ambient light washes out the blue. The plankton cluster only in these precise pockets, not in open ocean. In the Maldives, it's the quiet coves near coral reefs, where currents trap the glowing organisms. Globally, the phenomenon isn't random. It's a signature of healthy, complex ecosystems. When blooms peak, often in late summer, it turns entire bays into liquid light. You stand on a beach in Puerto Rico, watch a wave crash, the water shatters into blue sparks. It's not an anomaly, it's the ocean's hidden rhythm, a response to disturbance written in molecules. The light isn't the mystery. The mystery is why it happens asterisk here asterisk, asterisk now asterisk, in such perfect fleeting harmony. The ocean breathes, the light stays. The wave shatters. Blue sparks scatter where your foot meets the shore. Not a trick of the moon, not a reflection. The water itself is burning. You feel the cool shock as a wave pulls back, leaving a trail of electric blue. You bend down. A single drop glows in your palm, a living spark in the dark. The light isn't random. It's a chemical scream, luciferin and luciferase exploding in reaction to pressure. But why here? Why not in the open sea where waves crash constantly? The ocean doesn't scream everywhere. Predators, they say, a defense mechanism. But the open ocean teems with predators. Why does the chemical reaction only fire in Mosquito Bay's shallow lagoon 1-2 meters deep? Why not where the current churns? The predators are everywhere. The glow is nowhere else. The water is warm, 25 degrees C, rich with nutrients, yet the open coast, equally fertilized after rain, stays dark. The bloom clusters only where the lagoon's calm traps the plankton, not where the ocean swallows them whole. Nutrient runoff, they claim. Rain washes fertilizer into the bay, true, but every coastal storm delivers the same nutrients. Only Mosquito Bay glows, only the Maldives coves. The runoff is the same everywhere. The glow is a rare signature. The bay isn't just a location, it's a perfect trap. Shallow, protected, stable salinity, 35 ppt, no strong currents to disperse the plankton. The bloom needs the lagoon's specific stillness, not just the rain. What would settle it? Not observations, not maps, a genetic hunt. Track the exact dinoflagellate strains in every glowing lagoon. Are they the same rare species everywhere, or is it the asterisk combination of shallow depth, salinity, and the absence of disruptive predators in that precise pocket? Only DNA from every glowing spot, compared to dead zones nearby, could answer. The ocean breathes, the light stays. But why does it choose this lagoon, this asterisk night, over 1,000 others? The question hangs in the warm, glowing water. Why does the ocean save its light for only these places?